Yeah.
Someone share, let me explain.
Let me just close it.
Stop.
Remind me to give me back. Okay, so we're starting. Let the record show that we now know who Soy Boy is. It's Julius. And also let the record show that he has a very guilty look on his face right now.
Never can.
Okay, so today we're going to cover exponential growth and decay. What section is this? It's 2.6. 3.6.
Are we taking a quiz?
Huh?
Nothing else. Not I. That's all we can say.
So, an exponential, we say exponential growth. This means you grow at a rate proportional to your current size. So we spoke about linear growth a while back, and that was when you grew by a constant amount per unit time. The thing that distinguishes exponential growth is you don't grow by a constant amount, you grow by a constant percentage per unit time. A lot of things exhibit exponential growth, a lot more things in nature than exhibit linear growth, in fact. Population being a standard one. Things like compound interest also grow exponentially to some extent. So it's a very common thing to look at. Decay is sort of the opposite. It's when you decrease proportionally to your current size, and things like that would be like radiation and things like that would behave that way. So it's a very important kind of growth to talk about, especially in natural sciences. You'll see this sort of thing all the time. And you would see similar equations to this in your chemistry class, for example. So let's actually go through them. So these formulas here, I would expect you to have them memorized. They're in the box. They're very similar. One talk about growth and decay, and the difference is going to be the negative sign. So if we're talking about exponential growth, this means, let's say it's of the thing we're using to measure the current amount of the substance or whatever we're looking at is P. It tells you that the rate of change of P is proportional to its current size by a proportion R, which usually represents the percentage change. This guy is called the differential equation. It's called the differential equation because it's an equation with a derivative in it. Right? And so that's something you'd have to know. There might be a question where I specifically ask you, what is the differential equation that governs this growth? And that would be the equation you look at. It turns out we can solve this. To get the PERT formula. Turns out that P is equal to P naught e to the RT.
Wait, what's the?
That's
I've seen part, but what's the O?
so it's P naught, meaning it's the initial amount. Right? Now I could solve this for you guys, but it actually involves something called integration, which we haven't looked at yet. That comes towards the end of the semester. We look at integration, and I guess when we get there, we can talk about how we would derive this formula and where it came from. But for now, just know that this is called a differential equation. The solution to it, which you would get using integration, is going to be this one. It's called the PERT formula, and as a way to memorize that. So PERT like the shampoo. The game changer. The first ever shampoo and conditioner in one. I don't even remember when it came out. It was the 80s or 90s or whatever. But it was like, oh my god! They made a shampoo that's a conditioner as well? Like, I'm gonna save so much time! Yeah. And it was like, yeah, it was like a big thing. I know. Yeah, back when, this is back in the days of like VCR and vinyl records, like any little thing. Like, oh my god, the technology, I'm telling you, the world's getting crazy. Okay, so this is called the differential equation. This is the solution to the differential equation. P is the quantity of the substance that you're measuring. So that will tell you the current amount at time t. That's your initial amount. E is the number, E, that we've been using a lot. R is going to be the thing that gives you the growth rate. And that's going to be as a percentage. T represents time. All that is listed in the handout. So I'm not going to do that. One common mix-up is when we say rate of growth, you have to remember that we actually mean P prime. So if at any point I ask you for the rate of growth, I'm talking about P prime. The R is what's referred to as the relative growth rate. So they both have the word growth in it, so students get confused all the time. How about the relative growth rate? That's referring to the little r. Okay, so that's important for you to know. Now there are two things that, and at this point I can prove this to you. Now when you're talking about growth, you often want to talk about like orders of magnitude, like how long does it take to double something or triple something? Right? So if you talk about time to double, after how long will you have double what we started with? This is called, I denoted T with a little subscript D. We can actually solve for that. So this is, if we start with P naught, when will we have 2 times P naught? When will we have double of what we started with? And this would mean that I can set 2 P naught for the current amount, P naught for the initial amount. We can divide both sides by P naught. How would I solve that for time?
LN.
Put T in front of
I can ln both sides. In this case, ln cancels the E. And so we have ln of 2 is equal to RT. So this means T is equal to ln2 over R. And so that means the time to double is ln2 over R. And there's nothing special about the 2 per se other than it's double. If I wanted the time to triple, I would just put a 3 here and you'll have ln3 over R. The time to quadruple, ln4 over R. The time to become 5 times what you had before, ln5 over R, and etc. Right? But doubling time is something that we often care about, so that one I decided to mention the specific formula. Decay is very similar. The difference with decay is you put a negative power so that things decrease instead of increase, and you'll get all this very similar equations. I mean, I'm really flying through them here because 1, you don't need to know how to derive them, and 2, it's already written down in the handout. But if you're talking about decay, right, this means you're decreasing by a percentage amount per unit time. That means your rate of growth is a negative constant times your current amount. This means that you can solve for this to get P naught E to minus RT, and your half-life is going to be ln2 over R as well. All right, so all of these happen. This one is called half-life. And this is the time for half the initial, for something decreasing, half the initial amount to decrease, half the initial amount to remain. For those of you who are doing chemistry, that's something you would have heard of a lot. It's the half-life.
Where did the minus go?
Come again?
Why is it half-life negative? Yeah, where did the minus go?
Oh, well, we can solve for that.
It's the same as the growth.
It's exactly the same as the doubling time, it turns out. Because your R you'll always think of as a positive number and the negative sign comes out in front. And so if you have, if you want to find half-life, it means if you start with P naught E to the minus RT, you want to know how long does it take to have half of what you started with. Divide both sides by P naught. Again, you ln both sides. So you have ln of a half is equal to minus RT. And so you have T is equal to ln of 1/2 divided by minus R. And it turns out that that is equal to this. Can anyone see why this is equal to that? Why is ln of a half divided by minus R actually the same as ln 2 over R? Do you see why that's true? How can you rewrite ln of a half?
ln over 2.
Huh?
ln of 1 minus ln.
ln of 1 minus ln of 2 by the log rule.
Oh.
What's ln of 1?
0.
0. Log of 1 is always 0.
Oh.
So I get minus ln of 2. You can't forget your log rules. Over minus R, the negatives cancel, so you get the half-life is ln 2 over R. That's one of many ways to do it. You could also write a half as 2 to the minus 1 power and bring the minus down and cancel. You can get to that a bunch of ways. But at the end of the day, these are our equations. At this point, we don't know all the mathematical techniques to really play around with them a lot. So at this point, it's just a matter of memorizing them and using them as they come up. So if you look on the reverse side of the page that you have, which, by the way, all the handouts I'm giving you, they're all also online on the class website. But if you look at the reverse side, you'll see a list of problems there. And those are some very typical problems to ask. So if you have a problem that talks about exponential growth or decay, it will look like one of these guys. So usually it will have several parts. And you can also see something like this that was on the practice test already. But yeah, very typical kind of setup. So there will be something where we're talking about assume the rate of growth is proportional to its current size, or assuming something is radioactive, or assuming you have compound interest, compounded continuously, you know you have to do this. And so I believe I also, did I say that? So let's talk about when to use these equations. Let's mention that. So if you see phrases like grows, decays, proportional, to current size, if you see something like radioactive, we always assume that decays exponentially. Radioactive is exponential decay. You can also see, if you see phrases like compounded continuously, this applies. In fact, when I was sort of deriving the value for E, I talked about this idea of taking the compound interest formula, letting n go to infinity. You ended up with E. So in a similar way, you can get this, you get an exponential growth curve when you do the compound interest formula. But these are sort of hints to you. So whenever you see a word problem that talks about, well, it mentions any one of these buzzwords, you know you have to use these sets of formulas. So let's look at the first one. So let me read to you. So it says P is the current size of a population of a colony of bacteria at time t. At 10 a.m. there are 50 bacteria, at 3 p.m. there are 350. Assume the rate of growth of the population is proportional to its current size. So that sentence tells you you should be using exponential growth, that last sentence. let's talk about A. Find the relative growth rate of the population. And what's that? What is relative growth rate? So that's the little r. Right? And again, after you've done a few homework problems about this, you'll remember these formulas and you'll realize that relative growth rate refers to the little r. So we need to find the little r. How do we go about that? What information do we know so far? We do know the original. What was the original? We started out with 50, okay, and then what else do we know?
The time.
It goes
Current.
to 350.
Okay, so it goes to 350 when?
Is that PFT? After, from 10, yeah.
Okay, so how would you say that? How can you write that down?
What was T?
mathematically?
In seconds?
Sitting out.
Is T an hour?
No, times whatever.
Well, I didn't mention it here, but what would you rather judge it by?
Hours?
I mean, all the times mentioned in this problem is mentioned on the hour. I mean, if it's ever vague, I can mention it, but it seems to here that on the hour would be a good thing to do. But you can even say that at the end. So let t equal time in hours. So what else do we know if I consider that?
Oh, it's 5 hours. And 5 hours is 30.
So I know p when t is 5. I know p of 5 is 350. How can I use that information to find r?
We plug it in. The formula.
Plug it into which formula?
P naught.
Right, the PERT formula. So we also know that p is equal to p naught e to the rt. P naught we know, that's 50. E to the r we don't know, that's what we want to find. But I do know at a certain time. I know my t is 5, so I'll plug in 5 here. My current amount is 350, so that means 350 goes here. How do we solve for r?
Divide both sides by 50.
Divide both sides by 50. So this guy over here will give us 7. This is e to the 5r. How do we find r?
Ln both sides.
ln both sides. Here those are cancelled, so I get 5r is equal to ln 7, which means
Then divide by 5.
r is equal to ln 7 over 5. So that's my relative growth rate. Does anyone have a calculator? Can you tell me roughly what that is? Like on a test, I wouldn't care. You can leave it, but I just want to.
Will this be on our test when it comes out?
0.3891 or 3892.
0.38.
92.
Okay, so this is basically saying that this population is growing roughly 39%, by 39% every hour. Right, so that you can think of this R as the percentage measure of how something is growing. In terms of what's on the test, it'll be what the syllabus says, so I don't think this is in the test 2 section. So we're going ahead trying to get that bonus problem. Get that bonus. Okay, so that's that. So that was part A. Let's look at part B. Find a formula for P of T. So what would you say the formula for P of T is?
P of 0.
Just use the PERT formula. That's P naught e to the RT. And what you need to remember here is that there are really only 2 variables in this formula. There's P, which is the output variable. There's T, which is the input variable, which means E is just a constant. We already know that. So whenever someone asks you to find this formula, you need to find these 2 guys because they are constants, but you can determine their value. So all we're going to do is we're going to plug in these 2 guys. This guy we're given in the first sentence. This guy, the little r we actually found. So at this point, you just plug them in. So So it's 50e to the ln 7 over 5t. And that would be our formula for p. C. What is the size of the population at 4 p.m.?
P of 4.
What is p when
6.
at 4 p.m.?
So P of 6.
So, right, so 4 p.m. is when t equals 6, right? Because we're measuring, how do we know? Because they told the beginning was 10 a.m. That's when t was 0. We're measuring time in hours, and so that's 6 hours later. So basically, we want p when time is 6. And what do? We simply go to this and plug in the time. And that's the answer. So from doing the homework, see, what you're going to realize with these problems is the danger is making it too complicated. They're going to be easy, but every time an easy problem shows up on a math test, students get suspicious like, okay, that's all we have to do. That was way too. I definitely did something wrong. Then they erase it and do all this stuff. No, it's that easy. Just you find the formula, put 6 right there, and you're done. I mean, I don't even care if you plug that in your calculator. I would accept the answer as that. You don't even have to waste time telling me a decimal for that. So the hardest part in this sequence of problems, and we can talk about it towards the end when we learn about integration, but it's first recognizing when you need to use them and knowing what buzzwords refer to what things. So if you see relative growth rate, you should know that means little r. If you see rate of growth, that means p prime. Right? If you see find the current amount, that means the PERT formula, etc. So it's just knowing what each thing is referring to. D. What is the rate of growth? At 4 p.m. So what does rate of growth refer to?
It's P.
P prime, right? Because it's a rate, so it has to be some sort of derivative. How do you know it's not little r? Because it doesn't have the word relative in it. So there are 2 ways you would call the little r. Little r is relative growth rate. Another common phrase to describe little r is called the growth constant. Pretty much in every other case, there is p prime. Right, it's a very specialized phrasing for the little r, because it's not it's the growth that's governing in general, whereas rate of growth depends on what point in time you are. So we're using p prime equals rp, and we care about being at 4. So this means that p prime is equal to r, which we found r, so that's ln of 7 over 5, I believe that was. Yeah? And then this would be times the amount at 4. Which is what?
P of 6.
It's 4 p.m., so it's p of 6.
That's whatever we got.
And that would be the answer. Did we actually find that? Yes, we did. So we just plug that in. So this means that p prime is equal to ln of 7 over 5 times 50e to the ln 7 over 5 times 6. So So rate of growth would refer to P prime. We have a formula for P prime that's called a differential equation. That's just R times P. So I take R, which is this guy, and multiply by the current value of P, which is this guy. And that's it. E. When will the population reach 1,500?
Solid
When will P be 1,500 is the question. That's P is the current population. So the word when refers to what?
Time.
Time. So we know that time equals T. So to answer this one, we know we're finding a T value. So how do we get to that?
1,500 equals.
Right, we know that P is equal to 50 e to the ln of 7 over 5t. So we're just going to plug in 1,500 for this. And basically we want to solve for time. So I would divide both sides by 50. 50 over 50. What does that become on this side?
30.
Yeah, 30. So this becomes 30 is equal to e to the ln of 7 over 5t. Of course, we all know this game now with ln both sides, so we get ln of 30 equals ln of 7 over 5t. Then I divide t is just going to be ln of 30 divided by ln of 7 over 5, which I can flip and multiply. That's 5 ln 30 over ln 7. You can't divide these. You can't do anything with the 30 and the 7. Right? That's the answer. That's your t. Basically.
But if it was ln of 7/5, and the 7/5 was in parentheses, you can do that, right?
No. So if it was like ln 30 divided by ln of 7/5,
Yeah.
you leave it
You
like
leave
that.
that.
You don't do anything. But this 5 is not inside the ln, it's outside. So you can treat it like a fraction, flip and multiply, and that would be your answer. Not so bad, right? Is it? Okay. Let's do another one. Very typical kind of problem. I think the second example talks about half-life. Let's do example 2. So this one talks about half-life. So the half-life of a radioactive substance is 30 years. Okay. So they mentioned the word radioactive, they mentioned the phrase half-life, so you kind of know that you're talking about exponential decay here. So you see radioactive. So you know that you're going to be talking about exponential decay. So that automatically means you're going with the formulas in the second box on the first page. Okay. So we'll start about A. Find the differential equation satisfied by P. So what's that?
P prime equals negative RP.
In other words, we need to find this R. How am I going to find that R?
Oh, P prime over P. Negative P prime over P. P equals.
It's a constant, right? So P prime over P, we don't really know how to do that.
with the negative R.
How would you find R?
You replace P with P is 0 e to the
You want to plug into the PERT formula?
Yeah. So R is going.
Okay, well, if we go with the PERT formula, P is equal to P naught E to the RT minus RT. Do we have enough information here?
No, we don't have any.
Because I don't know a certain time what the value is, right? I do know in the beginning that I have 200, right? But that would mean time equals 0, I'd kill my R. I won't be able to solve for the R. So I have to be able to get to the R in another way. Yeah, the half-life equation, right? So don't forget that there are several equations that have R in it. Right? So there's this equation, but this equation is the one I want to find the R. The PERT formula gives me no information on finding the R, but we do know that the half-life is ln2 over R. So this means that 30, measuring time in years, is ln2 over R, which means that my R is ln2 over 30, which means P prime is equal to minus ln2 over 30 times P. And that's my differential equation. I was given the half-life, so I can find R using the half-life equation. It's always going to be ln2 over R. That gives the half-life. And know that that differential equation refers to this equation. So what's P? He says find a formula for P of T. I'll just call that P. What is that here?
300.
Well, we know we're using the PERT formula with a negative because we're decreasing, so that negative power is important. P naught, do we know that?
300.
It's 200.
200, sorry.
Suppose we have a 200 milligram sample, so that's what we're starting with. So the initial amount is 200. E to the minus R we just found in the previous one. That's ln2 over 30 times T. That's our P formula. How much will remain after 75 years? What do I do?
Plug in 75.
Plug in T equals 75, that's our time. So we want P when T equals 75. So I'm just going to plug that in. And that's the answer. After how many years will the mass be reduced to 1 milligram? How do you do that?
Plug in 1 for
One
P.
for P, yeah.
1 for P and solve for T. So that's again asking for the time. So we need to solve 1 is equal to 200 e to the minus ln2 over 30 times t. Solve that for t. So this would mean 1 over 200 is equal to e to the minus ln2 over 30 times t. Getting ln both sides. So ln of 1 over 200 is equal to minus ln2 over 30t, which means my t is equal to ln of 1 over 200 over minus ln2 over 30.
Bring the 30 up, right?
You can bring the 30 up because that's just a fraction. So your t is going to be minus 30 ln 1 over 200 over ln of 2. That looks negative. Is that negative?
You missed the negative.
Negative time? Does that mean? Huh?
Doesn't, yeah, you can't have a negative time, so does it not really matter?
Yeah,
Can you make it ln of 200 and cancel out the negative?
you can. So it's actually not negative, it just looks negative. Because this guy's a negative number, right? So this guy, the same way that ln of a half was just minus ln of 2, this guy's really minus ln of 200. And so this is really, I mean, this is fine, but you should recognize if you have negative time or positive time, because if you have negative time, it means you made a mistake. But you could rewrite this answer as that. You could also remember how the ln graph looks. It passes through 1 here. 1 over 200 would be over here. So ln of that is going to be a negative number. So there are a couple ways you can justify this answer. If you didn't have the negative, that would be wrong. So if you got to this point and you're like, oh my god, there's a negative, and you just kind of erase that, yeah, that's, that would be wrong. So you really have to be careful here. I mean, little nuances like that is the hardest parts of these problems. So you have to be aware that once you get an answer, it should make sense. And so when you see the negative here, you might have a knee-jerk reaction. It's time. Can it be negative? But the trick is it's actually positive because this part is negative. So that's actually the answer. It's actually a positive number. So don't try to be slick. What is the rate of growth at the time there is 1 milligram remaining? That's easy. Rate of growth when p equals 1. How do we find that?
Isn't rate of growth be fun?
Rate of growth is p prime. So we're going to use the fact that p prime equals minus rp, and we're just going to plug them in. So p prime is equal to r, we know it's ln 2 over 30. P, we're told that that's 1. So it's just that. Yeah, not very exciting. It's like once you learn how to find derivatives, everything's like, yeah, whatever, just plug it over there. Look like an expert now. Let's actually do just the last problem and we'll get out of here. So we'll talk about related rates the class after we get back. So when you come back, that's when we have the second test. The review for that is already posted. And the following class we'll go over the other handout that I gave you, related rates.
So the test is the day you get back?
Yes. Okay, so you have a mythical bank that pays 5% interest compounded continuously, because no one is going to pay you 5% interest compounded even yearly these days. So this means you're compounding, the interest is compounding an infinite number of times per year. Suppose you deposit $4,000 into an account with this bank. Write down the differential equation together with an initial condition whose solution is the amount in your account after time t. So the buzzword there is differential equation. So the first hint is the thing compounded continuously. That means exponential growth. In part A, they talk about the differential equation. So that's going to be p prime equals rp. The initial condition is just an equation that tells you how much you start with, so that's just going to be an equation that says something like p of 0 equals p naught, and then you fill in the numbers. So here we have p prime equals, what is r in this case? 0.05. So R is going to represent the percentage as a decimal. So that's 0.05 times P. And the initial condition is at time 0 we have $4,000. So that's your answer. So this part here is your differential equation. And this equation here is called the initial condition. So sometimes they ask you for one, but they can also ask you for both. So part B says, at what rate in dollars per year is your account increasing when the balance reaches 6,000? So basically they're asking for rate of growth when your balance equals 6,000. P is representing the current balance here. So what is that? So we know that P prime equals RP. So literally just plug in. R we know is 0.05. P at the point where P is 6,000, so I just plug in 6,000 and that's the answer. So that's the amount in dollars per year. How long will it take for your principal to reach 5,000? So you deposit 4,000. How long before you have $1,000 added to your money? And another problem I could have asked you here is, how long will it take to double your money in this bank? Right, so that's another possible question that I could have asked there. So C, how long until P equals 5,000? So you start with 4,000, how long before you get to 5,000? How do you compute that? At that point, just use the PERT function. You know P is equal to P naught E to the RT. This means I want this guy to be 5,000. I know I'm starting with 4,000. I know my R is going to be 0.05. And that's T. And now I'm just solving for T. So I divide both sides by 4,000. That's 5 over 4 equals E to the 0.05 T. ln both sides. So this means that ln of 5 over 4 equals 0.05 T. Which means T is equal to ln of 5 over 4 divided by 0.05. You can't mess with these numbers. This one is inside an ln, that one isn't. So that's your answer. And that's basically it. So there is calculus here, but it happens really in the background. And it involves integral calculus, so we'll talk about that towards when we cover integration. But for now, we'll stop there, and I'll see you guys when we get back.
Are we ending in 3.2?
Huh?